10 years ago, big data systems were built to collect terabytes of raw inputs and distill them into human-scale outputs, like a quarterly reporting dashboard. Today, training and operating large AI models requires a different supply chain. We now stream terabytes of data per second directly into GPU clusters to keep models running. Pushing data at this volume reveals a structural fracture. Architectures designed for human-scale analytics fail under the demands of machine-scale throughput. Trace the lag in modern AI infrastructure, and you arrive at the foundational open-source file formats currently holding the world's data. Specifically, the industry standard for the last 12 years has been Parquet. Its internal design now serves as a throttle on modern machine learning workflows. Parquet was built for a world of homogeneous, fungible CPUs. Dropping that format into a modern pipeline starves heterogeneous, high-bandwidth GPUs, leaving expensive hardware waiting for data to arrive. Fixing this at an exabyte scale requires a strict diagnostic vocabulary. Without a vendor-neutral methodology to isolate system failures, teams apply localized software patches to structural problems. This is the Datatism T7 framework, categorizing data system challenges into 7 distinct dimensions to identify root causes. For modern data ingestion, we isolate the intersection of T6, technology, and T3, transformation. The legacy file format dictates serialization logic that modern processors cannot efficiently transform. Resolving this intersection failure requires the file format to be rebuilt as an active compute engine. All software architecture is ultimately dictated by bare metal physical constraints, the speed of light, and hardware bandwidth limits. This is a logical schematic of a modern server node. You can trace the path from the network interface card through the CPU and the internal PCIe bus, terminating at the GPU. Historically, the speed hierarchy was fixed. The internal PCIe bus, connecting components on the motherboard, offered massive bandwidth compared to a restricted external network connection. Modern cloud architecture has inverted this. The physical bandwidth hierarchy is now flipped. On an AWS P5 instance, the network interface card can pull data roughly 8 times faster than that data can cross the local PCIe bus to the GPU. Parquet fails here. Its design requires data to route through the CPU for full block decompression before it ever attempts to cross that slow PCIe choke point. Operationally, the GPU cluster sits idle. The system starves while waiting for the CPU to churn through monolithic file blocks. Modern formats have a physical mandate. Data must stream straight from object storage through the network card and directly to the GPU, bypassing the local CPU choke point entirely. Vortex is a new file format engineered by systems programmers to exploit that network bypass. Its core philosophy relies on strict decoupling. Vortex separates the logical data type from where the physical bytes are actually placed in storage. This structural breakdown details the Vortex file topology. Working backward from the end of file marker, it sequences through the postscript, the flat buffer encoded footer, and the data pages. The first decoupled layer sits in the metadata, in a mechanism called layouts. Layouts are engineered to strictly defer I/O operations. Layouts act as out-of-core memory pointers. They embed a byte-level map directly into the file's footer, identifying exactly where specific data resides. Because this metadata is stored via flat buffers, the read scales in big O of 1 time relative to the number of columns you read. Parquet's metadata scales in O of n, which causes significant overhead on wide tables. By deferring I/O, the file becomes self-describing. A query engine orchestrates surgical byte range reads from object storage, pulling only what is necessary. The second half of the Vortex architecture focuses on deferring computation, utilizing a structure called arrays. Vortex arrays function as logical query plan trees that wrap compressed bytes. This allows computation to cascade over the data before it is ever fully decompressed. This design targets the strict execution rules of a GPU. GPUs operate on a single instruction multiple threads model, or SIMT, where hundreds of cores execute the same operation simultaneously across different pieces of data. The enemy of SIMT execution is a data dependency. Traditional high-ratio compression algorithms force processors to read previous bytes to decode the next ones, breaking the parallel execution model. This bar chart measures the decompression throughput of various algorithms running on standard hardware. This visualization tracks ClickBench and TPCH benchmarks, placing Vortex against Z-standard compressed Parquet on NVMe drives. For random access reads of isolated rows, Vortex operates 137 times faster. For full-scan decompression into an in-memory arrow format, it yields an 18 times speedup. These metrics prove that the engineering priority has moved beyond storage footprint. High-volume throughput is now the primary mandate. Raw speed is simply a byproduct of the engineering. The actual durability of Vortex lies in its extensibility. It is designed to be the LLVM for file formats, an open-source, industrial-strength harness capable of absorbing bleeding-edge storage research directly into production pipelines. By integrating WebAssembly, developers can compile new compression encodings and ship them forward in time. An older client reader can seamlessly execute a WASM function to decompress a new format variant. Returning to the Datatism T7 matrix, this structural flexibility resolves the diagnostic failure. The friction between legacy technology and modern transformation logic is eliminated. As AI models scale and hardware mutates, static file specifications will inevitably calcify into system bottlenecks. Solving the exabyte bottleneck requires formats that evolve with the hardware. The file must operate as an active node in the compute graph.